No financial interests or relationships to disclose. I will, however, welcome all of you to San Francisco. Hope you enjoy your stay here. Hopefully we keep the electricity on in this part of Northern California. So I want to bring you up to date with some of the emerging technology in accommodative IOLs. We've heard a lot about our multifocal options today. And this is really new frontier. So we do have three general categories of strategy for accommodative IOLs. We've got a change in optic position, that's the one we're most familiar with. But then we also have the option of what actually happens in the real world, which is a change in lens curvature on natural eye. But then we also have the option of changes in refractive index or optic power. And I just want to quickly go over the emerging options in these areas. We're obviously all familiar with the crystal lens product. That's the one with the hinged optic. But along the same lines of a single optic device that moves forward in space, thereby introducing a bit of myopia, we also have the Kellan Tetraflex, which has been around for a while, but still forging ahead. You can see it's essentially the same design as the crystal lens, one that has a 360-degree haptic structure with, again, a single optic vault is the Tetra in Irvine, California. The issue, of course, is that all of these devices are going to be limited by the fact that we have variable optic powers that we have to put in the eye for low myopes to high myopes to hyperopes. And that if you're dealing with an optic moving forward in space, number one, they don't move ahead very much at all. You're lucky if you can measure a millimeter, and it's probably going to be far less. And for most powers that are implanted, even if you can get a whole millimeter of forward movement out of it, you're going to get minimal accommodative change that is proportional to the power of the lens that's moving forward. So we have a bit of a problem there. So as we all know, it's far more efficient to establish your change in conjugation power through curvature change than by displacement. And you can model it out a lot of different ways. But if you take a 0.3 millimeter, as it were, shallowing of the anterior chamber from optic displacement from a 0.3 millimeter forward movement versus 3 millimeters in sagittal height change from a curvature change, if you model out a 20-diopter spherical lens, 6 millimeters in diameter, pick a refractive index, 1.4. If you go with that 0.3 millimeters of sagittal change, you're going to get about 10 diopters of accommodation in a curvature change system, hence the attractiveness. Now, probably the device that's been around the longest, Fluid Vision, is one that has these peripheral reservoirs, a distensible central optics, and with movement of fluid from the reservoir to the center, you get a curvature change. This is a device that I think was acquired by Alcon sometime back in March. Here in the Bay Area, one of the Foresight companies now is the OPR Device, and I should point out there is quite a bit of UCSF connection with that, though there's no financial tie to me or the institution. For Foresight Labs, run by Jean DeWan, has the OPR device, which essentially is a sulcus-based device with the haptics captured by the anterior capsule, and essentially it's an anterior optic that accepts the fluid, so that leads to the curvature change. That's pretty much the same approach that the Juvin has. I got these slides from Eric Donenfeld, and Eric was nice enough to provide them to me a few weeks ago. And this is, again, a device, as you can see, that has a compartment or a setup with the anterior optic, the one that again accepts the fluid transfer from the reservoir, and the posterior element is one that then remains available for refining the focus power of the eye or for a toric correction. This is essentially the same approach that Atia Vision has taken there in Canada. So again, they're a two-element device. The difference between the OPR and the Juvin compared to the Atia is that, as you can see in this diagram, it's actually the posterior element which is the accommodative element. And so the advantage there is that if one does need to go in and readjust the swappable optic, as it were, it's far more accessible since it's anterior rather than posterior. And this is an in-the-bag device as opposed to the OPR, which is a sulcus-based device. Finally, we'll talk about the options for change in refractive index or lens power. Probably the device that utilizes cubic optics that's been around the longest is the Lumina lens, which is based in Breda in the Netherlands. And essentially, this is one where, as you can see from the diagram, what you have are two elements with an interface between the two elements, which is a variable curvature, cubic optics. So you can see as the anterior and posterior surfaces are displaced relative to each other, that changes the power of the intervening space. And so essentially, with a bit of compressive effect from the ciliary body, you have relative motion of the anterior and posterior elements, and that leads to power change. The nice thing about these devices is that, again, based on the curvature that you impose between the two surfaces, you can actually get a pretty substantial change in conjugation power with minimal ciliary body effect. However, this does remain a mechanical approach. And so the big question is there some way that we can better utilize microfluidics or microelectronics to develop accommodated devices? And that's where we have sort of the really paradigm-shifting lens, the Sapphire. So this is actually an electronically based device where the trigger for this device is actually sensing change in pupillary diameter. So as you know, with accommodative effort, you get meiosis. So it actually picks up on the meiosis, which triggers the electronics to send a signal to introduce a diffractive pattern on the optic. So it basically switches on and off from a monofocal to a multifocal device. Of course, this has to be powered, and so essentially what it has is a remote recharging system. So you put these goggles on, these sleeping goggles, and then while you're sleeping overnight, it recharges the optic. It's large, it's heavy, it's definitely a first generation, but it's a very interesting device that's probably taking us very creatively and where accommodation may go in future. So, there's a lot being worked out there. We heard a lot about the various optical challenges and compromises that we have with anything that's a multifocal diffractive device, and so hopefully getting to the point that we can actually actively change the true conjugation power of the system with accommodated devices is something we'll have available to us in the reasonably near future. Thank you.